Thank you, Paolo, for inviting me and for the introduction. The project I'm going to introduce now is, it's Tâtonnement, approach to equilibrium and nexus volatility in firm networks. It's a project that started nearly, I think, over 2 years ago with first only with Jean-Philippe, and now we published a preprint just over a month ago with Théo de Sertène, Jean-Philippe, and Michael Benzaken. This is work I did while being part of the CFM Polytechnique Chair of Econophysics and Complex Systems too. I guess the main question that has interested me during my PhD and that still interests me is to try to understand what causes large macroeconomic fluctuations. So for example, if you look at this graph, what you have is the rolling yearly GDP growth in the United States. And you see that it really fluctuates wildly. And while I think, the pandemic has been a very complicated period, does allow me to give a very clear example, because you see in the end here that you see a very clear dip in GDP growth, which is natural. I mean, you have a very well identified, purely exogenous shock that can explain why you have this huge drop in GDP growth here. But when you look at all the fluctuations besides that one, it's not really easy to pinpoint what has caused these fluctuations. You see, for example, the late 2000s crisis here. And in the case of that crisis, it really isn't clear that there was some exogenous event, exogenous shock that can help you understand why you had these fluctuations. And in our view, it is that we think that most of these fluctuations that you see here are actually of endogenous origin. So they are they happen because of the intrinsic dynamics of the economy. And just to give you very quick numbers, as you can see, if you look at the average growth, you have 3.14% on average. You have positive growth since the 50s, but the standard deviation is of 2.6. And if you had a very naive view of the American economy, you would imagine that since you have millions of firms, you should expect that these fluctuations should average out in the end. And this is what constitutes the small shocks in large business cycles, as it was called by Ben Bernanke, the chairman of the Fed a few years ago. And so what people have, of course, tried to explain these fluctuations. And in the past, people, for example, if you look at Xavier Gabet, he proposed a model that, that he calls granularity, which is to say that the firm size distribution in all the countries where you observe, it's a fat tail distribution. So you have a lot of small firms, but then you have some firms that make up for a sizable chunk of the economy. So if those firms suffer fluctuations, so you can think, for example, of General Motors in the United States or Nokia in Finland, if they suffer fluctuations, then you will have large fluctuations at the scale of the country just because they make up for a large fraction of the country. But when you look at the data, you can't explain all of the fluctuations you see with just this granularity argument. So you would think that it's not reasonable to think that these fluctuations are independent of each other. And that is why people, first you had Long and Plosser, and then in the recent past you've had Acemoglu, and also for people like Vaso Carvalho, who tried to do network models where firms are interdependent. And for example, if you look at Acemoglu's paper, which was what kind of revived this idea in recent years, what they do is to look at the different economic equilibria in a network and to see how these equilibria move about when you shock them. So when you add exogenous shocks, I mean small idiosyncratic shocks to firms. But when you look at this picture, it's first off, because of the way it is technically treated, we think it's not general enough. And we also think that it lacks a dynamical picture, in the sense that what they are doing is looking at equilibrium, assuming that firms are always at equilibrium, and then seeing how that equilibrium can shift and move about. And so the model I'm going to introduce here tries to go beyond this and actually look for out of equilibrium dynamics, saying that firms may not necessarily go towards equilibrium all the time, or that they may just be swirling around it. So just to give you a very quick introduction into how you would do network models, it is a very simple idea in saying that firms need inputs from other firms to produce their own goods. And so the way you write this is that if you write pi I, which is the production output of firm I, then it is a certain function of all the inputs it gets from its suppliers. And then what you do is that you prescribe some shape for the production function. And so you have historically in economics, a very well-known function for this is the Cobb-Douglas production function, where basically you have this Zi component, which I'll be using a lot later on, which is what is called the productivity, and basically tells you how efficient you are in turning a certain amount of inputs into your output. You can think of that as a measure of how many inputs you can produce per unit time. And in this case, what the Cobb-Douglas function tells you that you have a product over your inputs. And basically you have these weights which appear as exponents of Qij, which are how easy I can substitute J with K. So if for example, if you're a car maker, with this production function, you can substitute tires with windows, for example. And so that is what was used, for example, in the Simobius paper. And what we use, and what has been used lately quite a lot in many models for this, is the Leontief production function, which takes the opposite direction, saying that you can't substitute inputs at all. So for example, in this case, you again have the Zi factor, that is a productivity factor, telling you how efficient the firm is. And then your production is going to be the minimum over the Qij, which is Qij is the quantity of inputs firm I has from firm J, divided by Jij, which is what we call it the stoichiometric coefficient that just tells you how many inputs from J you need for 1 unit of I. So just to give you an idea, for example, if I makes cars and J makes tires, then Jij is just going to be 4. And for example, if you have 1,000 windscreens, but you only have 8 tires, then you can still only make 2 cars. And that explains why you have the minimum over this. And so what I'm going to present to you now uses the Leontief production function for convenience, but the analysis we do is valid for a whole family of functions that interpolates between the Cobb-Douglas production function, where you have perfect substitution, to the Leontief production function, where you have no substitution. And in fact, the only outlier in this analysis is the Cobb-Douglas function. It's the only function for which this analysis doesn't really hold. But we think that in real life, there must be some non-substitution effects in how shocks propagate. So now once you have this, the question you ask yourself is to try to find the equilibrium. And basically you just say that firms can decide how much they will produce. So it's the output level, which is pi I, which I will show later on, can be written as Zi times gamma I. And you can also decide what price you're going to sell your good. And then basically you try to set these two variables in a way that you will maximize your profits, or equivalently, you will minimize your losses. And you will have also competition between firms driving those profits to 0. So at equilibrium, firms will not make any profit. And you also use market clearing, which is to say that all that you will produce will actually be sold to your clients. And then, well, in addition to this, we also have households which supply labor. So that's just another input. Labor is another input to our model. And so the household sells its labor, it gets a wage, and it uses that wage to consume the goods that are also produced by the firms. And well, I mean, you can say that it will decide how much to consume based on optimizing an utility function with a budget constraint, for example. That is one of the ways you can do it. You can also imagine different ways. And I don't really think it changes the analysis too much. But anyway, once you do this, so to actually do it quantitatively, well, you will maximize the profits, which you can write quite simply. So if you look at the top equation, so pi I is just how much I made times the price at which I sold it. So it's my net sales minus the sum of QIJ PJ. So it's how much I paid to my suppliers. And then, well, I call J equals 0 the household. So QI0 P0 is the cost of labor. And then you have to maximize this under the constraint that you're constrained by your technology, so your production function. And if you do this, you find that Qij must be set to be equal to a certain constant that is called gamma I, which is what actually sets your production level times the Jij. So if you look at this, it just tells you that if you look at the production function Zi mean of Qij over Jij, it just tells you that all of the Qij over Jij will be equal to gamma I. So you will not be buying anything more than what you need for your production. And so once you do this, you can actually take the top equation, rewrite it, and we'll set the profits to 0. And if you notice here, you can write this as a matrix equation with this matrix M that is basically going to be have the Zi, the productivity factors on the diagonal, and the off-diagonal coefficients are going to be the Jij linkages to other firms. And so you get this linear equation with V, which is a vector that has positive components, which is basically the wages you had to pay your labor needs from the household. And you can do the same thing for market clearing. So basically, again, you're just going to write your own production. So Zi gamma I is how many goods you produced minus what you sold to your clients, and that should be equal to CI, which is the household's consumption. So here I'm just saying that what I produce is going to be either sold to my clients or sold to the household. And you also get the same equation with the same matrix but transposed. And the thing is that these equations, if you want to solve them, they should, for this thing to make sense economically, you should get positive gammas and positive prices. And because of the shape of the matrix with positive terms on the diagonal and negative terms on the off diagonal, you can show that for you to have actual positive solutions for this, you should have the positive part of the eigenvalues of this matrix M should have a positive real part. And so what this means is that there isn't always an equilibrium. And what I will use from now on is epsilon, which is going to be the eigenvalue of M that is leftmost in the spectrum. So if all the eigenvalues are real and positive, for example, then epsilon is just going to be the smallest eigenvalue. And if this thing becomes negative, then it means that you cannot find prices or output levels anymore. And so it means that equilibrium will not really exist in that condition. So in a paper I wrote with Jean-Philippe, we showed that basically the dynamics you can have within the economy can push this eigenvalue close to 0 or even negative, and it can cause this equilibrium to disappear. And we interpret this as crises. And here you can think of this as separation between two timescales. So you have a very fast timescale at which firms set their prices and their output level. And then you have a very slow timescale that in a way you would say in physics you consider to be frozen, which is the scale at which the network or the productivity changes. And so in the past, what we focused in is imagining that equilibrium is always reached, it's instantly reached, and then you just change the network. So you change the equilibrium and you see if the equilibrium can be attained or not. So that is what we did at first. And now in this work, what we did is actually introduce dynamics for the prices and the outputs to see if this assumption that equilibrium is reached is valid or not. And the way we did this is to use very heuristic and phenomenological arguments for the dynamics and the decision rules that firms will use. And basically, what we will say is that firms will try to find this equilibrium using trial and error, which is what tâtonnement means in French, dynamics. So what we did at first is create a very, very naive, very simplified version of these dynamics, just because it's one way of making this problem analytically tractable and to gain some insight for this. Although the model I will show afterwards is more complicated, it's basically just it has the same core ideas of this. So what do firms do? So as I said, firms control the price at which they sell their production and their output level. And you have two sources of friction to this, which is profits. So you can make a profit or lose money, and market clearing too. So you can make more goods than what you manage to sell, or you can produce less than what people demanded from you. And the idea we had is just to say that the way the prices would progress is, well, you see here you have excess demand on one hand. So it's how much you manage to sell divided by your total production. So in this case, for example, if you produced more than what you could sell, you will lower your prices in the next time step. And that is why what this term with the alpha in front of it does. And then you also have some friction with the profits. So that is just a way of introducing artificially competition between firms. So if you make a profit, it will eventually tend to drive your prices down because of competitiveness with other firms. And then below what you have is the profits again and the excess demand. So in this case, the term with the beta tells you that if you made a profit, you will tend to increase gamma, because if you made a profit, you will say, I just want to produce more, to sell more and to make more money. And you see that in all cases, if you have excess demand to zero, so if market's clear and if the profits are equal to zero, so if you have a competitive equilibrium, then you will reach a fixed point. So the previous analysis acts as a fixed point to these equations. And well, so you know what the fixed point is. And so the next step you can do just to understand the dynamics is you can linearize around the equilibrium points. So around the fixed points as I described before. And so if you write delta P and delta gamma for the distance to these equilibrium values, you can linearize the problem with this U vector that captures all of these gaps to equilibrium. And using this stability matrix du, where you've just linearized the dynamics. And you can actually relate the spectrum of the matrix M I showed before to the spectrum of this matrix D. And you can see that essentially you know that this system is stable if the eigenvalues of D all have negative real parts. And this is actually, you can show that this is the case when the matrix M has positive eigenvalues. So if the equilibrium exists, then in this case, it is locally stable. So far, we're only doing linear analysis, so very close to equilibrium. We know that it's locally stable. But in our previous argument, what we said is that there's a lot of reasons to think that this epsilon eigenvalue is very close to zero. And actually, you can show that the smallest eigenvalue of D is also related to epsilon. So you will have an exponential decay towards equilibrium, but the time scale at which this at which you reach equilibrium is actually 1 over epsilon. So if epsilon is very close to zero, it can actually take you an astronomical time to reach it. And so you see that this idea of always thinking around equilibrium is not necessarily valid in this framework. And you can also actually augment the model by imagining that you have these linearized dynamics, but you also add in some stochastic noise. And in this case, what happens is that if epsilon is small enough, then you keep shocking the system, but the system doesn't have the time to relax back to equilibrium. So you keep being shocked away from equilibrium, and the variance in this case will not be given by sigma, which is the variance of the noise. It will actually be given by 1 over epsilon, something proportional to 1 over epsilon, so the smallest eigenvalue of D. So that is one mechanism to have excess volatility in this network framework. So when we built this model, well, we simulated it. We got all of these analytical results, but it still wasn't really satisfying because it's not realistic. It's in a way it's too linear. For example, we don't really say what happens when you don't produce as much as what was demanded from other people. So in a way, you can have negative fluxes of goods between firms. And the other thing was that while the linearized analysis worked rather well, we still didn't really think it held well outside of the basin of attraction of this equilibrium. So we got on to build a full-fledged ABM where you have different steps in the decision process of the firm. So firms will actually have to forecast how much other firms will want to buy from them. They will then have to set the targets of production. And based on how much they think they will need to produce for the next time step, they will post demand. So they will tell other firms how much they want to buy from them. And so this information will circulate, and you'll have a production loop. And on the other side, you also have you also have labor markets. So you have to hire workers depending on how much you want to produce. These workers then also have different wages and so on. So it's got very simple ideas, and the model is quite heavy, so I don't really think I have the time to go all the way over it. So I just want to give you some key ideas behind what we did with this. So for example, again, comparing to the naive model I just presented, firms still control their production. So they still get to choose how much to produce and how much to sell it for. But to do this, they will actually have to anticipate how much they will have to pay for their input. So anticipate the prices of their suppliers. And they will also have to anticipate how much they will be able to sell. So they have to anticipate the demand of their clients. So the way we prescribe that firms do this is very simple. So we just say that firms will extrapolate from the past trend, or they'll use the current price as a proxy. So for example, it's two different types of behavior. But for example, if I noticed that the price at which I managed to sell my production from the previous time step to this one increased by 10%, then I just say I think that my price will keep on increasing by 10%, and that will be my forecast. Or another simple forecast you can make is just to say that the price tomorrow will be the same as the price today. So we implement these different decision rules. And based on that, then firms decide, well, they say, okay, I will produce this, I will aim to produce the certain amount that will be given by this quantity gamma hat at time t+1. And the caveat here is that it can be different to what you actually manage to produce. So if just as a topical example, you can say, I will produce 1 million vaccines next week, but then maybe you didn't have enough, you didn't manage to buy enough vials, so you will only make 500,000 vaccines, even though your target was different. And then based on this, they tell their suppliers how much they will need from them. And they may also keep some inventories of unspent inputs they didn't use in the last production time steps. And so once you do this, so you decide on a certain target, and so you ask, so you are firm I, and you ask firm J for a certain quantity Q hat that you need to meet your target. And you ask for this based, and you set this amount that you need from J. And you may also keep some inventory IIJ. And so the quantity you will actually ask of J will be this QIJ that you will actually demand it, which is going to be given by this quantity. So for example, if your inventories are sufficient, then you will not ask anything to J. That is why you have this max of IIJ minus QIJ. And otherwise, if you don't have any inventories, you will just use, you will ask for all of the QIJ hat. So this is what you ask, but this is maybe in fact different from the amount that J will actually manage to sell to you. So for example, if you look at this quantity QJI, which is which is it's the symmetric. It's what I will be able to sell to another firm J. Well, what you actually do is that you take the demanded quantity and then you multiply it by the supply over the demand. I mean, the minimum of one or the supply over the demand. And what this does is very simple. It basically tells you that if you produce enough, so if you have a lot of your own good to sell to your clients, then you will sell your client exactly the amount that he demanded. And if you didn't manage to sell enough, then you will just sell a fraction of this quantity that is going to be weighted by by the supply of the demand. Okay, so this is one of the features of this model, and this is one of the aspects. So here it's just the how we handle demand. But what I want you to understand is that these nonlinearities appear everywhere in our model, and we think that they're actually rather realistic. I mean, if if a firm didn't produce enough in real life, then she will not be able to supply its clients very well. And these nonlinearities, as you will see too later on, are also what can cause very, very curious behavior that is very different from what you expect from the previous model with the linearized dynamics, where basically what you imagine you will see is just an exponential decay towards equilibrium. And just to give you a hint into what happens, what goes on in the model is, well, the workers' wages also have to be updated depending on the tension on the labor market. You also have, so the household must also decide how much to consume, and they will do this by also extrapolating how much they will be paid in the next time step. So the household also has to do its own forecast of how wages will evolve, just as the firms have to forecast future prices and so on. And well, I mentioned inventories, and well, we do keep inventories, and they may decay. So if you don't use something, then a fraction of it may disappear in the next time step, just because it may perish. And what is interesting is that the way that you do this timeline of the decision process of the firm is actually important in how to describe the stability of the system. And another point is that we also have the update parameters, so describing how you forecast and so on. And they are very similar to the alpha beta parameters I described before. And you actually recover, in certain regimes, you recover the same behavior I described before. So again, with the epsilon, again, with the exponential convergence, depending on certain regions of the parameter space. So you can actually get a lot of different behaviors from these simple rules. So for example, when actually epsilon is positive, so epsilon is the eigenvalue of the matrix that describes the firm network, you do see some relaxation towards equilibrium. So this is a delta p, so the distance to equilibrium. You see that you have an envelope, an exponential envelope, and then a decrease that goes down. So you do relax to an equilibrium that does exist when epsilon is positive. You can have oscillations or not, depending on the spectrum of the linearized matrix, which you can also compute. And then what happens when you have negative epsilon is, so when epsilon is negative, as I told you, there is no fixed point. You know that there isn't. And what you see is, so you can see these oscillations. So you see they may be limit cycles, they can be chaotic, they can be synchronized, desynchronized. You can get really a lot of behaviors depending on the different parameters you choose. And because also of the nonlinear effects that I mentioned with minimums and maximums appearing everywhere, you can also get spontaneous crises. And well, if you're curious about this, I can give you a very short explanation using also maybe some ideas from matrices into why this happens. But you see that the system seems to be stable, and then poof, you have a huge crisis that blows up. And you can also give this a test. So I don't think I have time to show the simulation, but you can click on these links. And the first link is so it's just a dashboard where you can pick the parameters and run the simulation and see for yourself that you get this type of behavior. We also published the code to the ABM on this GitHub repository. And so we also summarized the different effects that you can get from the parameters. So again, you have two parameters. For example, here it's alpha. So it's how you will update prices depending on your production surplus. So depending on your excess demand. Or for example, omega, which is the sensitivity of wages to job market tensions. And you see that you get this phase diagram where depending on where you are, you can get, so you can go to equilibrium on the light blue region, you can have crises or you can have cycles and chaos. So we do have this in the paper. And to wrap this up very quickly, the remaining questions we have is to try to find a systematic way of studying the different phases I just showed you in phase diagram. We also hope that our model is sufficiently well specified at the micro level that we may be able to calibrate it with existing data now. And in the end, something that interests me in particular now, very much, now that I'm also part of INET, is to try to find observables that can maybe help you understand and discriminate for different causes of business cycles using real data. So that is personally my goal in the midterm, I would say. And with that, I finished my presentation, and I thank you for your attention. And if you want the references, so it's the link that Paolo sent you on the email for the first paper, and then you have these other two papers that may also be of interest to you. So thank you.